Kirchoff's junction rule is really just an application of a conservation law to electric circuits. We've talked a little about conservation of energy and about conservation of momentum. We haven't talked really much about conservation of charge, which is one of the other conservation laws, that if we have some charges, then the amount of charge doesn't change. And think about what the charges come from here. They're electrons, right? So if we have a certain number of electrons moving at one point, we have the same number of electrons moving at some later point. This is another case where the thinking of electrical current as water current, I think, is really a pretty good analogy. So if we imagine some river that's flowing in this direction from top to bottom of the screen, and we have a fork in the river, so some goes off to the left and some goes off to the right. I think we can pretty easily see here, however much water we have moving through this branch, that has to be the same as the amount through this branch plus the amount through this branch. So if we have, say it's a little tiny river, we have 100 gallons per minute flowing through this area. Maybe this has 40 gallons per minute. This one must have 60 gallons per minute. If this one were only 50 gallons per minute, that would mean that every minute 10 gallons of water are just winking out of existence. Or, okay, evaporating. So actually this could happen with a river. So we'll ignore evaporation for the time being here. But the amount of water moving through each point in the path of this river has to be the same if we ignore evaporation and we ignore water soaking into the ground or whatever. Now if we follow this down a little bit further, and we see that our river rejoins here, and we had, what do we say, 40 gallons per minute this way, 60 gallons per minute this way. We get back to this junction where the two combine, and we get now 100 gallons per minute flowing through this one single path. So this splitting of paths idea with a circuit is going to get us to a little bit more complicated circuits. We see in this circuit we can have current going, we go from the positive side of the battery over here. At this point we have a split. Our current has to kind of make a choice. Do I go this way or do I go that way? And you may have heard the term the path of least resistance. The current will follow the path of least resistance. That's sort of misleading here. You might think, well, whichever one has a smaller resistor, all the current's going to go through that path. It's actually going to be a split. More of the current goes through the path with less resistance, but still some of the current, just less current, goes through the path with more resistance. So we have some that goes through this path and some that goes through this path. So we might have go through here and back, or we'd have it go through here and back. And so we could think about the current or measure the current at different points here. So let's say I measured the current right here, and I'll call that I1. And then we have this split. We'll say we have a current I2 here and a current I3 here. So we know that the current has to be the same in total all the way around. And so we could write here that I1, since it gets split into I2 and I3, those two have to add up to just I1. So I can write I1 equals I2 plus I3. And then here we still have I2, here we still have I3, and you might think, well, gosh, we go through this resistor here and this resistor here, don't we lose some of the current there? Well, no. The only way that we can lose current, if that's even a correct term, is if we have current splitting off into a different path, into a different channel. So here, it doesn't matter what components we have in these circuits, the amount of current doesn't change until we have this splitting of paths or recombination of paths. And so we'll get I3 coming back this direction, and then right here we have another junction. Junction is just the general term we use for any time we have a split or a combination of different paths of the circuit. So I2 and I3 come together at this junction, and we leave with I1 again, the total current, I2 plus I3. And that goes all the way back to the battery, I1, and all the way out of the battery, I1. Now the trick on these ones is going to be figuring out, well, first off, how much current do we have altogether. We've done Ohm's law to find current, I equals V over R, or rather delta V over R. But here we have two resistors, so which one do we use? Or do we add them together? Do we average them? Or how do we handle that? We'll get into that with the discussion of equivalent resistance in a later video. We will find, though, that we can pretty easily find I2 and I3 once we've found I1. And so we'll be getting back to Ohm's law here. So this junction rule is more of a conceptual thing, that we don't have charges disappearing or appearing out of nowhere, so the current can split and it can combine, but we can't change the amount of current. But we also can write this mathematically as an equation, and that's an important and useful way to think about this as well.